Welcome to the Deep Dive. Today, it is just us and you, the middle school science educator.
Yeah, we are so glad you were joining us for this one.
We have a pretty substantial stack of your sources on the table today, honestly. We're looking at NGSS foundational frameworks, EQIP guidance rubrics, pedagogical architectures, and some assessment matrices.
It is a lot of dense material to get through.
It really is. But our mission today is to take all that density and use it to completely rewire how you view the science and engineering practices.
Yeah.
The SEPs.
Right, because usually, when you walk into a traditional science classroom, there is this expectation of like a museum exhibit.
Oh, that is a good way to put it.
Yeah, you look at the posters on the wall, the teacher points to a static diagram of a cell on the board, and the students are essentially just visitors.
Right, they just read the placards and memorize the vocabulary.
Exactly, they move on. Science is presented as this completely finished product.
Neatly packaged and, sealed behind glass. But the moment you step into the world of the next generation science standards and really broader three-dimensional learning frameworks, that museum closes permanently.
Yes, it becomes an active, noisy construction zone.
Which is exactly what we want. We want to help you shift your mental model today so you see these 8 SEPs not as extra enrichment tasks you do on a Friday or, isolated skills.
Right, they are the active doing and thinking engine of how your students actually make sense of phenomena.
Because the traditional focus was always memorizing what science is, right? But the authentic focus we are aiming for is understanding how science is done.
So true. And to really grasp how that shift happens in, say, a 7th grade life science course, we have to look.
First, you have your disciplinary core ideas, the DCIs.
Which is the actual content students are trying to understand. Things like genetics, cell structures, ecosystems.
Exactly. Second, you have the cross-cutting concepts, the CCCs. These are the broad thinking lenses applied across all fields of science.
Right, like looking for patterns or mapping out systems and system models.
Yeah. But then the third dimension, the SEPs, these are the verbs.
They are. They describe the actual behaviors that scientists and engineers engage in to investigate the real world.
Because students can't just learn about an ecosystem, right? They have to participate in the science of uncovering how it works.
Exactly.
So, I like to look at three-dimensional learning, kind of like a kitchen. The disciplinary core ideas, your content, those are your raw ingredients. You have your flour, your eggs, your yeast.
Okay, I'm tracking with this.
And the cross-cutting concepts are the flavor profiles you want to achieve, like sweet or savory. But the science and engineering practices, the SEPs, those are the actual cooking techniques.
Oh, wow. Yeah, the chopping, the sautéing, the baking.
Exactly. You can have all the ingredients in the world, but if you don't actually do the cooking, you just have a pile of raw flour. You don't get a meal.
That totally makes sense. And taking that kitchen idea further, think about the cognitive shift that requires.
What do you mean?
Well, in a traditional classroom, the cognitive burden is entirely on the teacher to explain the recipe, and the student just has to recall it. They memorize the phrase, the mitochondria is the powerhouse of the cell.
Oh, the classic middle school science phrase.
Right. But when you bring in the SEPs, the burden of sense-making sheds entirely onto the student's shoulders. They have to actively use these practices to explain how energy actually flows through the whole cell system.
But to make sense of a system, a 12-year-old needs a starting point. They need a spark to get that engine turning. How does a teacher actually initiate that?
Well, that initiation relies heavily on the first two practices. SEP 1, asking questions and defining problems, and SEP 2, developing and using models.
Okay, let's start with SEP 1.
So science and engineering are distinct here. Scientific questions help us investigate the natural world, whereas engineering problems identify human needs that must be solved within specific constraints.
But middle schoolers already ask a million questions. Like they come in asking, why is the sky blue? Or what happens if a black hole hits the sun?
They really do.
So how do you take that raw, chaotic curiosity and actually shape it into SEP 1?
Well, when a kid asks a broad why question, the teacher's immediate move should be to ask, well, what could we measure to figure a piece of that out?
Oh, I see. That forces the shift.
Exactly. Your sources emphasize that by 7th grade, students must move past simple descriptive curiosity. They need to formulate empirically testable questions.
Questions involving specific variables, right?
Yes. So instead of asking, why do some birds have big beaks, they need to be guided to ask, how does the size of the seed available in the environment affect the survival rate of birds with varying beak sizes?
That is a huge pivot. It changes the entire trajectory of the lesson.
It does, because a testable question inherently demands evidence.
And once they have that question, they need a theoretical vision of what they think is currently happening. Which brings us to SEP 2, developing and using models.
Right. And your sources call models thinking tools that help students transition from concrete to abstract thought.
So what does that actually look like in a 7th grade life science class?
You'd use multiple types of models. You might see a diagrammatic model, like students drawing a food web to trace energy flow,
Okay, sure.
or physical models, like using interlocking connectors to demonstrate DNA-based pairing. You might even use computer simulations where students manipulate variables to see bird beak evolution in a virtual environment.
Or even mental analogies, right? Like comparing a cell membrane to a security guard.
Yes, exactly. All of those are models.
Wait, hold on a second. I have to pause and advocate for the classic middle school science experience here.
Uh-oh. What did you make?
I definitely brought in a shoebox. I painted a styrofoam ball green. I stuck some pipe cleaners in it, labeled the nucleus, and I called it a cell. And I got an A. Are you saying my beautiful styrofoam diorama isn't a true scientific model?
Well, according to the EQAP guidance rubrics in your sources, it is absolutely not a model. I'm sorry. It is an art project. A scientific model must be used to explain phenomena or make predictions.
Wait, really? So just showing the parts isn't enough?
Not for SEP 2. If I ask a student, based on your styrofoam model, what happens to the cell if I introduce a toxin that destroys the mitochondria, and the model cannot help them reason through that answer, then it is not functioning as in SEP.
Oh, wow. Okay, so a useful model must actually reveal gaps in understanding.
Exactly. It has to break or change when new evidence is introduced.
So a model is really just a working hypothesis. It's a guess about how a system operates. But, I mean, a theoretical model only gets you so far. Eventually, that mental framework has to collide with reality.
Which is where the student has to break out into the real world to test it. And that leads to SEP 3, planning and carrying out investigations, and SEP 4, analyzing and interpreting data.
Okay, let's look at SEP 3. Investigations are structured ways to gather actual evidence to see if the model holds up, right?
Yes, exactly.
But if I am the teacher, and I am not allowed to just hand them a worksheet with step-by-step lab instructions, how do I keep a room full of 12-year-olds from turning a science investigation into absolute chaos?
That is the fear, isn't it?
Do I just say, go investigate and hope for the best?
Not at all. Bounding the investigation is key here. You don't hand them a cookbook, but you do provide a menu of constraints.
Okay, a menu of constraints. I like that.
Yeah, 7th graders need to learn to identify independent and dependent variables, and they need to learn what constitutes a fair test. You might give them the goal and the available materials, and they have to decide what data matters and how to collect it reliably.
You know, the sources also make a point that not every investigation requires a formal wet lab with safety goggles and Bunsen burners.
Right. Designing an investigation might just mean setting up the parameters of a computer simulation to track resource availability and population changes over 20 virtual generations.
So the practice is really about the logical structure of gathering evidence, regardless of the physical tools used.
Exactly. It's about deciding what data actually matters.
And gathering that evidence generates a lot of raw information, which pushes us directly into SEP 4, analyzing and interpreting data.
Yep.
So I kind of compare data to raw puzzle pieces. Like, collecting them during an investigation is great and all, but until you snap them together to actually find the patterns, you don't see the big picture.
Oh, that is the perfect way to look at it, because data really does not explain itself.
It's just a pile of pieces.
Exactly. Finding the picture requires deliberate scaffolding. The NGSS framework expects 7th graders to do some pretty sophisticated sorting.
Like what?
They have to find patterns in data displays, distinguish between linear and nonlinear relationships, and critically learn the difference between causal and correlational data.
The sources actually highlight a classic 7th grade scenario for this, which is studying moth populations.
Oh yes, MSLS44.
Right. So instead of the teacher just standing at the front of the room saying, hey, moths adapted to their environment, the teacher hands the students a scatter plot showing moth survival rates over a decade of environmental changes.
And look at what is happening cognitively in that scenario.
What do you mean?
The student isn't just reading a summary. They are actively interpreting the story the numbers tell about genetic variation and survival probabilities. They are pulling the biological concept out of the raw data themselves.
Oh, wow. Yeah, they're snapping the puzzle pieces together. Okay, so the student has found a pattern. But Spotting a trend on a graph doesn't mean much to the scientific community unless you can mathematically verify it and translate it into a concrete explanation.
Which brings us to the next two.
Hmm.
Step 5, using mathematics and computational thinking, and Step 6, constructing explanations and designing solutions.
Now, Step 5 often triggers a lot of anxiety for science educators, doesn't it?
Oh, absolutely. The matrix of connections to the nature of science shows us that mathematics is integrated into these practices, but we really have to be clear about its purpose.
I can literally hear our listener thinking this right now. I teach life science, not algebra. My 7th graders are already stressed enough. If I lean heavily into Step 5, aren't my students going to panic that biology has suddenly become math class?
I mean, it is a totally valid fear, but the math in the SEPs is strictly a tool for clarity, you know?
Okay, so it's not just doing equations to do equations.
Exactly. It is about quantitative thinking. Can a student figure out the average of a data set to confirm the trend they think they see?
Or like, can they identify a statistical outlier in their plant growth measurements and decide if it was an error or an actual discovery?
Yes. The math is there entirely to strengthen a biological claim.
It clears up the noise even further. And once that noise is cleared, we reach Step 6, constructing explanations and designing solutions. This feels like the massive cognitive payoff of the entire process.
It really is the culmination of their investigative work. A scientific explanation answers the how or why a phenomenon happens using valid evidence.
And an engineering solution solves a problem under specific criteria and constraints. The sources mention the CER framework here quite a bit. Claim, evidence, reasoning. It's pitched as a highly effective scaffold for middle schoolers.
And it is. You make a claim about the phenomenon, you back it up with specific data from your investigation, and then you provide the scientific reasoning that bridges the two.
But there is a catch, right?
Definitely. CER is a fantastic tool, provided it doesn't devolve into a mindless formula.
Right.
If students are just filling out a graphic organizer, checking boxes to get the assignment over with, without actually thinking about the biological logic connecting their evidence to their claim, well, we are back in the museum.
Back to rote compliance.
Exactly. The reasoning section must be deeply grounded in the disciplinary core ideas.
Constructing a valid, evidence-based explanation is a huge achievement for a 12-year-old. But out in the real world, a scientific explanation isn't accepted just because it's written down neatly on a CER worksheet.
No, it is not.
It isn't accepted until it survives the scrutiny of peers.
The crucible where ideas are tested, which requires Step 7, engaging in argument from evidence, and Step 8, obtaining, evaluating, and communicating information.
I find Step 7 fascinating because, well, middle schoolers naturally love to argue.
Oh, they do.
But scientific argument is not about who can yell the loudest or debate an opinion. I view it a bit like a courtroom trial.
Oh, I like that analogy.
I mean, the group evaluating the claim isn't looking for the most charismatic presentation. They're looking for the strongest evidence and the most airtight logical reasoning to support the claim.
It is a mode of logical discourse. Students use argument to evaluate competing design solutions, challenge the premises of a classmate's claim, or identify weak reasoning in a model.
Like, they might argue over whether a specific change in water temperature actually caused a population drop or if it was just a correlation.
Right. They are learning that disagreement is incredibly productive as long as it is grounded in evidence and respectful reasoning.
Which naturally leads to how they interact with information generated by others. SEP 8, obtaining, evaluating, and communicating information.
And in today's digital environment, gathering information is effortless. Evaluating its credibility is the actual challenge.
Let's say a student brings in a short video from social media claiming a new diet alters human DNA within days, and they ask if it's true. How does a teacher use SEP 8 in that moment?
Well, instead of just saying, that's fake, the teacher uses the SEP to ask, how do we evaluate the source of this claim? Does their explanation align with the models of DNA we've built? Where is their data?
Wow, turning it back on them. Can the students synthesize information across different texts to verify it? Can they spot skewed data or pseudoscience?
Exactly. In a world of infinite information overload, SEP 8 is arguably the most vital, high-stakes life skill these students will take away from a 7th grade science class.
The ability to consume information critically and communicate truth?
Yes.
Well, we have covered an immense amount of ground today walking through this entire three-dimensional engine.
We really have.
For the educator listening, the core takeaway from your sources is that these 8 science and engineering practices are not a checklist to speed through. They are the essential verbs that define how your students interact with the natural world.
Right. By embedding these SEPs into the daily rhythm of your curriculum, you empower your students to stop being passive observers in a museum and start being active sense makers.
You're equipping them with the cognitive tools they need to figure out the world, not just memorize a glossary of terms.
And designing instruction this way takes time and deep pedagogical thought. But watching a student truly grasp a complex biological system because they investigated it themselves is, honestly, the most rewarding experience in teaching.
Congratulations on doing the hard work to make that happen. But before we sign off, we want to leave you with a final provocative thought.
Something to turn over in your mind as you look at your upcoming unit plans.
If we are completely shifting the classroom so that students are actively doing science through these 8 practices, if they are modeling, investigating, snapping puzzle pieces of data together, and arguing from evidence, how might our traditional grading systems need to fundamentally evolve?
Ooh, that is a big question.
Right. If the learning is in the process of their reasoning, how do you capture that in a gradebook rather than just scoring the final answer in a multiple choice test?
It really challenges the very foundation of how we measure student growth.
You just cannot grade an active, messy kitchen the same way you grade a silent museum. Thank you for joining us on this deep dive. Keep pushing boundaries, keep asking great questions, and we will catch you next time.